Okay, so welcome back to lecture 4 of deep neural networks. And as we have said many times, the topic that we will cover today is stochastic optimization, the actual form of gradient-based learning that we typically do in neural networks. And today I'm going to talk a little bit about practicalities, but I think I'm going to be focusing more on why we are doing it and why it might be useful. So there is a ton of other resources on the internet if you are practically interested in picking up tricks like how do I set the learning rate or how do I tweak the parameters of these algorithms. To be fair, I don't know much about that myself. There are many students of mine who will be able to help you much more with that. So we will focus at a very high level what it is and what we have learned about this in the last couple of years. So what we had said about neural networks so far, I'll try to move this because it's somewhat annoying. Maybe less annoying down there. So what we had said about neural networks is that we train them using gradient descent, and we talked about how we calculate gradients of the empirical loss or the loss averaged over your training data points, how you kind of optimize the parameters of a neural network that way. And I had this up on one of the slides before, which is how we obtain the next parameter vector W at time step t+1 from the previous one is we just subtract some learning rate eta times the gradient. Now, if we actually did it this way, it would be very kind of difficult and impractical, because if you want to work with large data sets, then you would have to cycle through your whole data sets to calculate this sum. And even maybe more importantly, we want to calculate these, as Nick will talk about. We want to calculate these things on a GPU or a specialized hardware, not on the CPU, which means that we need to have the data that we are going to use to calculate this data set on the memory of the GPU or on the memory of the device. And that's usually limited, and particularly used to be very limited compared to CPU memory. So it was just impractical to actually calculate this gradient over your entire data set because you couldn't fit that data set into the memory. And it's also wasteful. Like fundamentally, you don't actually need to calculate this entire loss gradient here, because as L hat is a sum, it's not apparent from this form, but if you remember, it's obviously a sum or an average over data points. The central limit theorem applies. So this, the actual value of the gradient as you keep adding more and more data points, and average over more and more data points is going to converge. So at some point, if it converges, you can just cut that off and not calculate it for all of your data points. For all of these reasons, people have actually done something else, which is stochastic gradient descent. And this particular form of gradient descent is mini-batch gradient descent. What changed is that instead of evaluating the loss on the whole data set D, I evaluated on D sub T, which is a smaller subset of my data set. It's a random subset or mini batch of my data. And usually we sample these mini batches by chopping the data set up and then cycling through those mini batches of data. So this is what we practically do. And for all of these practical considerations, we have been doing this forever in deep learning. So the first question that you might want to ask about this algorithm, does it converge? The same way as gradient descent, we know it kind of converges to a local minimum, or maybe it gets stuck in a saddle point in weird cases, but we know that it converges. If we actually calculate only the gradient on a small data set each time, we introduce some approximation error or noise into those gradients. Does that approximation error hurt us, or does it still converge? And I think last year when I did this, I ended up trying to sketch a proof of the convergence. I don't think it's actually that meaningful, and I kind of got confused and it took a long time. So just take my word for it, roughly how you would, for those of you who are into stochastic processes or probability, the way you would reason about why this stochastic optimization method converges is by first observing that because this loss evaluated in a small mini batch is an unbiased estimator of the loss on the entire data set. We can make this argument that if you take sufficiently small step sizes in the direction of this random gradient, then the empirical risk in expectation does not increase. So the empirical risk at the next step is going to be a random variable because you're taking a direction in a random gradient. You're subsampling your data randomly. And that random variable has an expectation, and that expected value, the expected loss at the next step, is lower than the loss at the current step. And for processes that have that property that the expected value at the next step is lower than the current value, is called a super martingale. Sounds very amazing if you haven't heard it yet. And then there is a theorem which guarantees that if you have a super martingale, which is kind of a stochastic generalization of a decreasing sequence, and it has a lower bound, which is it cannot go lower than a certain value, and for loss functions this is usually guaranteed, then you're going to converge to something. So that random sequence of losses over time in the stochastic process is going to converge to some number. It's not necessarily going to converge to a minimum. The loss will converge, which means that, for example, you might be going near a minimum, but because of the randomness, you might be jumping around that minimum quite a bit. And the average value of the loss remains the same, but you do not actually converge into the minimum. So that can happen in stochastic gradient descent. But if you keep decreasing the learning rate, so you take smaller and smaller steps, then eventually even that is guaranteed that you will end up converging to a local minimum of the empirical loss. We can ask a second question now that we know that it converges, or you believe me that it converges. Does it behave in the same way? Like, does it how is it different from the deterministic gradient descent when you take all your data at once? And here are two scenarios. Imagining that now this is a cartoon illustration, not an actual optimization problem, obviously. The x-axis here is my parameter. Let's say that it's one-dimensional for easy illustration. And the y-axis will measure the loss function. And I assume that there are two scenarios. In the first scenario, let's just talk about the left-hand side first. The yellow line is the average loss. If I average it over all my data, I would get the loss surface, which is or loss curve, which is the yellow curve. And then if I evaluate this loss on random mini batches, say batch 1, batch 2, batch 4, batch 1 again, apparently, then I would get these noisy versions of the loss curve, maybe, and some of the data points, the loss looks a little bit different. And I can imagine a different scenario on the right-hand side, which is, again, the curves mean the same thing, but now, maybe in this scenario, I have the same kind of average loss surface, but now when I evaluate it on different batches, I get a slightly different signal as to where the location of the minimum is. And these curves are like not so, they're a little bit more different from one another. And, but on average, I assume that they still give you the yellow curve, so that, on average, the loss functions would be the same thing. So this would be, for example, the situation if you use a large batch size. If you use a large batch size, because of the central limit theorem, things are going to converge and look more and more similar. And this might be the situation when you're using smaller batch sizes for the opposite reason. But it is also possible that within the same learning problem, within the same loss function, this is non-convex optimization. You can have multiple minima, and it may be that one of the minima behaves like this and the other minimum behaves like that. So it's not just a function of the batch size. It can be a function of anything else. And so in this situation, when the variance across many batches is small, so large batch learning, the behavior of gradient descent and stochastic gradient descent is very similar. So every step you would look at one of these curves and you would evaluate its gradient and take a step in the opposite direction. It's going to push you this way. Then I take, say, the blue curve, it's going to push me this way. Then I take the other purple curve and push it this way. Sorry for all the colors pretty much looking the same. I don't know why I chose these colors. But essentially, the way stochastic gradient descent is going to proceed is going to be pretty much how gradient descent would proceed. In the second scenario, there might be differences, because now let's say that I start from here and I evaluate batch 1, and I again don't have batch 3 for an interesting reason. So I evaluate this blue batch 1. It's going to give me a high gradient because it's a steep function. So it's going to say that the minimum is this way, take a large step this way. And so I'm going to go this way. Maybe I evaluate now this dark blue curve. It's going to still say, go this way. And maybe now the next mini batch, the purple one, is going to say, hey, wait a minute, now the gradient points in the opposite direction. It's going to send me back the way that I came from. So there could be a lot more like jumping backwards and forwards. And of course, if you imagine this being in high dimensions, it could send you in like arbitrary directions. And another thing that can happen if the different mini batches give you conflicting signals is that sometimes these gradients can be very large, and they might just send you completely out of the vicinity of this minimum. So it may be that stochastic gradient descent just cannot properly converge to the minimum value, which is somewhere here, because one of these gradients just ends up so large that it's going to like send you away, and you would converge to a different minimum instead. Whereas it's a little bit less likely to happen in a situation like this. So it's just a cartoon illustration of how stochastic gradient descent might behave slightly differently from the usual gradient descent, just because of this extra noise in the gradients. The basic version of stochastic gradient descent, which I had on the slide, has been improved in many ways. So you can kind of identify different problems with stochastic gradient descent or gradient descent and try to propose different ways to fix them. Usually fixing it means that I design an algorithm that converges more robustly or that converges faster. That's what I mean by improving it. The first idea that a lot of these improved methods use is momentum. Who has heard about momentum in optimization? Probably more than the number of hands I'm estimating. So some of you have. There are usually the story that we give, motivating story we give for why we want momentum is twofold. In stochastic gradient descent, I told you about this, the gradients might have high variance. So sometimes it points in this direction, sometimes it points in that direction. And you don't really want to always go in that random direction. If you take too large steps in those random directions, you're just going to end up like noisily sampling in parameter space. So you somehow want to reduce that noise or want to reduce that stochasticity. And then the second situation is this oscillation in a narrow valley, which there is thankfully, okay, how do I find this? Hopefully this is still shared. So thankfully there is this very nice blog post, or it's not even a blog post, it's an article about, just trying to make it bigger. Okay, I think it's big enough. This nice interactive article illustrating why momentum works. So what you're looking at here is a loss surface in 2 dimensions. Darker values mean lower value of the loss. So you want to end up in the optimum, which is shown here. And this illustration always shows you the same number of gradient descent steps. So each of these dots is starting from here, each of these dots is a gradient descent step. And so I'm going to turn off momentum here. So there's going to be a parameter that allows me to introduce momentum, which I haven't talked about yet. And I also have this step size parameter, which is my eta from the slides. They call it alpha here. So if I start from a 0 learning rate or step size, I'm just never going to get anywhere because I'm not taking steps of 0 size. And if I start very, very gradually increasing it from 0, I will start taking very, very tiny steps in the direction of the gradient. So in this case, there is this valley, and I'm at the kind of mountain next to this valley or whatever, hill next to this valley, and I start to like very slowly go down this valley. If I increase the step size, I will eventually reach the valley and I start going towards the minimum. However, what happens if I increase the step size at some point, I'm going to take a large enough step down this hill that I overshoot the valley. Instead of going into the valley, I end up climbing the other hill on the other side of the valley. And then I have to kind of take a step back this way. So I start this slight oscillation. And if I increase the learning rate again even more, then these oscillations can be very big. So instead of going down the valley, I'm just going to climb higher and higher on the hills either side. And if I do this to the extreme, then you get very weird behavior, these oscillating behaviors. And this can happen in gradient descent. If you use large step sizes, this oscillating behavior just keeps sending you farther and farther away. And notice that for no value of the step size do I reach the optimum in the number of steps that I have. Okay, so let's start from this step size because it kind of gets far enough or close enough to the optimum eventually. The idea of momentum is to say, instead of paying attention to these individual gradients, I'm going to average them over time. If I take the average of this gradient and this gradient, the largest components of these gradients are perpendicular to the direction that I actually want to move, and these oscillations will start canceling each other out. So this moving in this direction and then the gradient pointing in this direction cancels each other out. And if I take the average of these first 5 gradients, it's going to look, I'm going to be left with just a component of this vector that actually points in the direction that I want to move in. So this is basically what momentum is. And this beta parameter controls how much of the past gradients do I incorporate in that moving average. So if beta is 0, I'm going to forget all the past gradients. If beta is 1, then, or close to 1, I'm going to keep an infinite memory of all the gradients. And so each next gradient is going to have a smaller and smaller effect on which direction I'm actually going. So if I start adding some momentum, you can see that as the motivating thing predicted, the oscillations decrease. And it also allows me to kind of accumulate this momentum. This is why it's called momentum, towards the minimum, because in the direction where you have consistent gradient signal, consistently all of these gradients kind of go to the right. So this momentum allows you to recognize that that's the direction. Another thing that I can now do is, if I have momentum like this, I can now increase the learning rate without the whole thing blowing up, or it kind of blows up at some point. But if I add big enough momentum, that compensates the effects of a large learning rate. So I can converge to an optimum faster, and notice that I didn't add any more steps. And just by adding more momentum and slightly increasing the learning rate, I could now get to the optimum in the same number of steps that I couldn't get to without the momentum. Now, as the title of this article probably already suggests to you, this is only part of the story. This narrow valley story is the typical story that we give to motivate momentum in almost every lecture about momentum in optimization. But this is a several pages long, very nicely written paper that actually motivates why it's just part of the story, and momentum actually has all of these weird behaviors that you wouldn't expect it to have. And it can have its own oscillations. So if you crank up the momentum all the way, then you can see that it introduces its own chaotic type, or oscillating type behavior. And it's also not practically very useful. Okay, so this is about momentum. And let's go back. So the problem was high variance of gradients due to either stochasticity or because of this oscillation in the narrow valley situation. And the solution is to maintain a running average of gradients and then move in the direction of the running average. The second idea for SGD and non-convex optimization in general is adaptive step sizes or adaptive learning rates. And to motivate why this is a problem, in a neural network, there's this weird mapping between the parameters of your neural network, these W's and B's in the expression, and the actual function that the neural network implements, which is the input-output relationship of the neural network. And some of those weights are going to be very influential in defining what this input-output relationship is. And this influence can be measured by the gradient. If I change one of the parameters just slightly, maybe my entire function changes what it does. Suddenly it thinks that whatever it thought was a cat before, now it thinks it's a dog. So some of the parameters will have very high gradients, and some other parameters might become completely irrelevant to whatever the function is doing at the moment. So you can maybe get rid of that parameter, set it to 0, or you can multiply it by 10, and the function doesn't really change too much. And so there's this imbalance between some parameters receiving very high gradients and some parameters receiving very low gradients, or kind of they're not that important in the optimization objective. And so setting the learning rate is difficult because you can't set a learning rate too high, because then those important units that the output function is sensitive to, they are going to go crazy. You're going to have high gradients multiplied by a large learning rate. You're going to take 2 large steps, and you're going to end up in this oscillating regime. But if you set the learning rate too low, then those units where you have small gradients are just not going to move at all, because you have a small gradient multiplied by a small step size. You're just going to be super slow, and they're going to get stuck in their values. But you somehow want to intuitively achieve a situation where all of these parameters are moving at roughly the same speed over time. And this motivates the desire to set the learning rate specific to each of these parameters. And roughly so that the learning rate cancels out the magnitude of the gradient. So you somehow want, if the magnitude of the gradient is high, you want a smaller learning rate for those units. And this is exactly what most of these adaptive step size algorithms do. In addition to maintaining a running average of the gradient direction, which is what momentum does, you also, for each unit or each parameter, you maintain a running average of gradient magnitudes, which can be like the norm, the Euclidean norm of the gradients, or the squared of the gradient for that specific one value. And then you use the inverse of that accumulated gradient magnitude, so 1 over that number, as your step size for that parameter. So essentially you divide your gradients by the average magnitude. So after the division, the steps that you're going to take are roughly going to be the same size for all of your parameters. And if you take these two ideas, one being momentum, maintaining a moving average of the direction and moving in that direction, and adaptive step sizes, which is maintaining a moving average of the gradient magnitude and normalizing the step size by that, you get this algorithm called ADAM, which you're going to come across at some point if you haven't already several times. This is probably the most used optimization or variant of stochastic gradient descent in deep learning. So the details here are not that important. This is from the original ADAM paper from maybe 2014-ish. What you will notice, I think, is that the magic happens kind of here, or not really magic, but the moving averaging happens here. So you have the previous, the direction of the movement m, and you take this exponential moving average, which is take the previous value multiplied by some coefficient smaller than 1, and you add in the new gradient gt. This is going to be an exponential moving average here. And the higher this beta value, the more you remember the previous value. And if you set beta to 0, then there is no memory. Then you're just back to normal memory-less gradient descent, or momentum-less gradient descent. Okay, who has come across ADAM before? Hands up. Okay. Good, Neil. Do you use them in Gaussian processes?
No, but it probably is a Gaussian process.
Sorry, this is
it's got a second
inside joke.
Moving average, so
it must be. So ADAM if you are doing anything with machine learning, probably the first optimizer you want to try using is Adam. It's implemented in all the different deep learning packages. And the reason for that is because it works very well out of the box for many problems that you want to work on. And working out of the box means that it's not very sensitive to how precisely you set the learning rates. It's not very sensitive to how you initialized your networks. Most of the time, if you use these packages and you initialize it using the standard initialization, you come up with something, Adam is going to do something. It's not going to get stuck out of the box. Whereas the vanilla versions of SGD can be a little bit of work to get to work. So maybe the learning rate is too small, nothing happens. Learning rate is too large, nothing happens for the opposite reason. Whereas with Adam, you get this nicer behavior. But to answer how good Adam is as an optimizer, or part of a machine learning optimizer specifically, there are two different ways of answering that question. And initially, we mostly thought about the optimization aspect, which the optimization aspects are how fast it converged or how robust it is. And from an optimization perspective, Adam is really good and better than SGD usually. But there is also a secondary aspect, and we talked about how we now consider it. You now consider the specific optimization algorithm we use part of the learning algorithm, and that it can influence the generalization properties of the entire machine learning system. So we don't just care about how fast we converge to a solution. We now also care about, are we converging to a good solution or a bad solution? And so we can ask us an almost opposite or orthogonal question about Adam, which is, does it tend to find solutions that are better than SGD or worse than SGD? And the first paper that asked this question in an empirical setting is this one from 2017. It's called the marginal value of adaptive gradient methods in machine learning. And from the title, you can probably guess that the answer is Adam is not actually as good. There are some downsides to using a better optimization algorithm. Here are the main findings from this paper. The different colors show different optimization methods. SGD is the most vanilla version of SGD. HB is heavy ball. I'm not going to talk about that, but it's anyway, I'm not going to talk about it. Adagrad is adaptive gradients. So it's a version of Adam without the momentum term, roughly. RMS prop similarly. And then we have two versions of Adam here, the default parametrization that just comes out of the box, and then one that has been tuned to this problem specifically. And for all of these optimizers, we use exactly the same training or neural network architecture and exactly the same data set. CFAR10 is a relatively small data set with just 10 classes and thousands of examples in each class. I think this is kind of used a lot when studying things at ImageNet scale wasn't really feasible, like back in 2017 or 2016 times. There are a couple of interesting things from here. Can anyone tell me why we are seeing these staircases? It's not difficult. It's also not trivial. If anybody has seen them before, feel free to say it. I'm not going to be. Anyone seen them before? Just put your hands up if you've seen these staircase-like optimizations. Okay, some people have seen them. And do you know? Sorry for now you're trapped.
I'm not sure about Adam, but the one that I was doing was the step size. I was using flatters.
Yes, yeah, that's the correct answer. So the answer is that the step size is changed. So one trick that we sometimes use, particularly in stochastic gradient descent, and here it's used, I think, for all the algorithms, is that we are changing the learning rates as we go along. We start from a high learning rate, and then you can see that look at here. So it's start from some learning rate, we make quick progress, but then at some point we stop making progress. The learning rate is too high, we just go around in circles. And at that point, when the progress slows, we say half the learning rate. And then we can make faster progress again, because now we are kind of zooming in to the finer details of the loss landscape. That's the intuitive explanation here. And we do that several times over during the training process. That's a typical practical trick that people use, particularly in computer vision. And another thing that we see is that in this specific example, Adam with the default parametrization did not perform very well. It actually did not reach a very low training error. But if you optimize it, it becomes the second best on the training set. So the left one is the training set error. SGD kind of found the lower minimum, but this one is Adam. It's not doing particularly poorly either. But what's important is that if you look at the test error, which is when we evaluate these methods, how well they did on held out test data, we see that SGD, and notice that the y-axis changed and it's no longer from 0. So, you know, this the lowest performance is actually just 7.6. SGD does significantly better on the test data compared to these other methods like Adam. Adam does something like 12% error rate, which is about 50–60% higher than what SGD does. And so the moral of this paper was that even though SGD has all of these nice properties, if you actually invest the energy or sort of time to find the best possible parameters for the vanilla versions of stochastic gradient descent, you actually end up with a better performing solution. It's easier to get Adam working reasonably out of the box, or with like a little bit of fine tuning, just like trying 3 different learning rates and pick the best one is usually like good enough. But if you really want to squeeze out the best performance from your models, then the vanilla version of SGD tends to work better. And that's a practical thing that people do nowadays. So when you try a new method and a new benchmark, you use Adam to experiment with your methods, to try many things quickly. And then once you are happy with whatever you want to fit to the data and how you want to fit it, then you switch to SGD and you try to find the best hyperparameters, best learning rate schedule, best everything else. And usually SGD is the final method that achieves the performance that people report in the papers. So revisiting this cartoon example, remember the 2 different minima that you might find in a problem. One where all the mini batches kind of say the same thing, and the other one where the mini batches disagree, but on average, they would produce the same average loss. And I said that SGD has a difficulty converging to minima like this because there is high variance, so it might just be catapulted out of the vicinity of the system. So now, I actually wanted to bring a very nice chocolate bar that's from like responsibly farmed cocoa and everything, and I left it at home. So I got a protein brownie from the sports center. So if anybody can venture an explanation or just guess an explanation or guess, if there are these 2 minima, which one might be better for generalization? Which one might we prefer from a machine learning viewpoint, from the viewpoint of generalization? And like any kind of heuristic argument is welcome. You have a protein brownie. This is your chance to put on some muscle mass. The left one because more of the batches, yes. And why do you think that's important for generalization? If the batches agree on the minimum. Yeah. It's more, yeah. So if the batch is kind of all smaller data sets, all think the minimum is at the same location, then there's sort of disagreement. There is agreement on the location of the minimum. I'm gonna not throw this at you because that can go wrong. Another sort of thinking it a little bit further, generalization about whether finding the minimum on the training set will mean that you also found the minimum on the test set, or you're close enough to the minimum of the test set. So you can make this argument that if in this case, choosing different mini batches of my training data doesn't really matter in terms of how my loss function looks like, then maybe if I chose those mini batches from the test data instead, I would also get very similar curves. So maybe I can predict that the location of the minimum on the test data is also near the location of the minimum on the training data. Whereas here, if I subsample my data and even small mini batches of data cannot agree about what's going on, then probably they also won't agree with whatever the test data thinks is a good solution or a bad solution. So this, there is this heuristic argument to motivate why actually solutions like this, we don't want them. We don't necessarily want to find them. And the story here is that Adam fixes the kind of the problems with SGD, and Adam makes it easier for SGD, or the modifications in Adam make it easier for SGD to converge even in situations like this, by the use of momentum, by the use of adaptive step sizes. And so now Adam can converge to minima that we think may not generalize so well. So maybe it's going to converge faster, but it's going to converge to a minimum that has this type of properties, which we actually didn't really want to converge to in the first place. So by fixing some problems for optimization, it might actually counteract some of the beneficial properties of SGD. Maybe it wasn't such a bad idea after all that SGD has a difficult time converging to minima like this. Maybe that's kind of a feature, not a bug. So, so far this has been a very cartoonish, intuitive explanation for what SGD does and does not do. So I wanted to show you that there is now, actual mathematical, I wouldn't say theory, but mathematical illustration of these same phenomena. This is the paper that I talked about last year, and then it was a very fresh paper. It came out just 2 months before we ran this course last year. Oh no, not even actually, just a month before. Now it's a 1-year-old, it's a classical paper now in deep learning. And it's the title is on the origin of implicit regularization in stochastic gradient descent. So implicit regularization is about this, I call them inductive biases before, this like tendency of SGD to favor certain solutions over other solutions. And this is a nice mathematical analysis of how we can how can we understand what SGD is doing differently compared to the basic versions of gradient descent. And this is a very bird's eye view of this paper. What we are going to look at is, here is some parameter space, and we can look at batch gradient descent or full batch gradient descent. This is when you use all your data points. It's impractical to run, but you can reason about it mathematically. Compared to this, stochastic gradient descent is a stochastic process. And I illustrated this by drawing these circles. So if you start from this location here, after the first step, because you follow the random mini batch gradient, you will end up at a random location. And from that random location, you step in another random direction to an even more random, so to speak, direction. And you kind of end up, the more steps you take, the more random it is where you end up, kind of. And so this is a very difficult process to understand because it's a stochastic process. So one simplification that they made in this paper is, let's just look at where the mean of this, of all the possible places that I can end up after, say, 10 iterations. Where is the mean? Where is the expected location that I end up after 10 iterations? And that again becomes a deterministic thing that I can now calculate and compare to this deterministic thing with gradient descent. So this is the analysis technique that they use roughly. So mathematically, if this is SGD, again, this is stochastic because I evaluate the loss on a mini batch dt, and I can look at the expectation of WT, and I call that mu t. This is the mean iterate. And the expectation here is taken over different ways I could shuffle my data, or the different random seeds I could use to determine how I shuffled my data. And I'm not going to go into how they got this result, but roughly what they show is that this mean iterate in SGD stays very close to the solution of this differential equation. I don't know if you study differential equations much in Cambridge computer science. Do you? Does that come up, differential equations? Okay, it does. It kind of must, but I was hoping. And this looks a lot like what is called gradient flow, which is a very simple way, very simple differential equation where some parameter moves in the direction or opposite to the direction of a gradient of some scalar function. So this mu t moves in the opposite direction of the gradient of some scalar function, L tilde of SGD. I'm going to talk about what it is. Yeah, and I think the important thing is, what is this L tilde of SGD? If I have a gradient flow like this, just like with gradient descent, I'm going to end up with a local minimum of this scalar function here. Or maybe I can end up in a saddle point. It's very unlikely, but usually I end up in an optimum. And the key finding here is that if I look at what this function is for SGD, it ends up being the function that I would get for gradient descent if I used all of my batches of all of my data, plus this term. And for those of you who are quick at reading math, you will maybe notice that this is something like the variance of gradients. So just to go through the points here, this thing here is the gradient on the whole data set. This is the average gradient across all your mini batches. And this is the gradient on just a single mini batch dt. So this is a random variable whose mean is the right hand side. So I have a random variable minus its mean, and I'm looking at the expectation of the square of that, which is like the variance. It's a little bit of an odd thing to say is the variance of gradients, because gradients are high dimensional, but it's the trace norm of the covariance matrix, if you want to be very precise. And this is great, because now I can say that this is a precise relationship under the assumptions of this paper. It says that stochastic gradient descent is like gradient descent, but instead of following my loss function, it follows my loss function plus this extra regularizer term, or plus this extra penalty term. And this extra penalty term penalizes me for going into parts of the loss function where the different mini batches disagree a lot on the gradient direction, where there is a high variance of the mini batch gradients. So notice that this means that the minima of L tilde SGD is different from the minima of L tilde GD. And in particular, if you go back to this, Okay, if you go back to the cartoon example, let's say that these are two minima of the same learning problem, and the minima are exactly the same value. So neither of them is deeper than the other. They are also the same shape, so we can talk about like this is a wide minimum and this is a narrow minimum. But gradient descent, according to this penalty is going to make, sorry, there's, I don't know why it's slowing down. Whoa, okay. So this minimum, which is in the region of high gradient noise, is going to incur a higher penalty in that expression before. So this is going to look like a worse minimum compared to this minimum. And so SGD is going to be much more likely to converge to a minimum like this one. So now, in addition to this intuition, there is now at least a mathematical illustration or some sort of mathematical explanation for why and to what degree SGD favors minima where the mini batches agree. And I'm not going to talk about that too much, but there is also some theory that then connects this property of minima, which is called stability, to generalization. So why minima that behave like the left-hand side are actually better at generalizing. You can formalize that as well using math. And if you're interested in actually digging deep into these, just to advertise, in the Part 3 or MPhil course next year, there's going to be a theory of deep learning module, which in which we are going through, like this is one of the papers that we are going to like go into details on. And also the double descent, which Neil showed, is we have even a paper on triple descent. Kind of the latest and greatest on generalization research. Okay, so we have this, this connection between stochasticity in training and generalization. Is this necessary? Or is it just like a nice to have? Can we turn off the stochasticity and can neural networks still learn something? And this is a paper that came out relatively recently, I think maybe a couple months ago, which I don't like the title because I don't think that's what, I don't think the title actually describes what the paper's details say, but it's sort of a claim that's saying that stochastic training is not necessary for generalization. So to illustrate what these people did, I think they used to be anonymous. Now we actually know who the authors are. Never mind, I should update those slides. So I mentioned that we do stochastic gradient descent for practical purposes. We can't just cycle through our entire data set. And they said, we are Google, presumably. We have lots of resources. We are actually going to cycle through all our data in every iteration of gradient descent. So they spend enormous computing resources and a lot of time to actually perform full batch gradient descent in neural networks just to find out what would happen if you did not have the stochasticity. Would it still work? So that's pretty nice. I don't actually know if they're Google, but sort of extrapolating from the amount of computation they do. And this is the main set of findings that they have. We have the stochastic gradient descent baseline with mini batching. So you have the mini batch based stochastic gradient descent, training it for 300 epochs, which means that you cycle through your data set 300 times. This is CFAR, the same data set that we used, that we talked about before, maybe CFAR 100, which is the larger version. And then this is the number of gradient steps that you take overall. Obviously, it's much higher than for the full batch gradient descent because you take one gradient descent for each mini batch. And that achieves a validation accuracy, which is kind of like the test performance of 95.7%, which is good. If you use full batch, FB stands for full batch, not Facebook, just to mention the other company. There's no mini batching. You do 300 epochs like before, but in every epoch, you take just one gradient step on your whole data set. So 300 steps. That performs terribly, 75%, which is not bad, but it's also not, it's not nowhere near what you should get. First thing that they try, what if you do full batch, but now you train longer because now, for each epoch, you only do like one gradient step. So if you do 10 times as many steps, 3,000 epochs, then it starts to become better, 87. And then they start adding all kinds of different tricks. And these tricks become very interesting, particularly in the light of the previous paper and finding that we discussed. First thing that helps is clipping gradients, which is like you would imagine, if the gradient is above a certain value, you just clip it, so you set it to the maximum value. You don't allow too large gradients. And this usually helps. We even use it in SGD. Second thing they do is they regularize, and the regularizer they introduce tries to find wider minima. So minima where the roughly where the Hessian of the loss is, the eigenvalues are large, small. I'm looking at you.
Yeah, the covariance is the inverse.
Yes.
The last covariance.
Yes. So small eigenvalues. Neil briefly talked about how the Hessian of the loss at the minimum might be indicative of generalization. So this is where this regularizer term comes from. That starts to achieve better performance. And then the final thing they do is this BS32, batch size 32. Here, this is full batch. So there are no mini batches in the training, but in the loss function, they simulate the effect of what if we did batch size of 32 by estimating the variance of gradients, this term that appeared in the previous paper, by chopping up the data set into these 32 length mini batches. So essentially, instead of implicitly running SGD, which implicitly kind of does this, you explicitly code this up and you explicitly like make this your loss function. This is what the BS32 regularizer does. For some reason, it really doesn't want to go further than this slide. And that's when you get all the way to the top performance. You can actually beat baseline SGD with that. Neil?
It's a bit weird, right? Because they've used all these tricks to recreate the conditions of stochastic gradient descent much more expensively.
Yeah, so they recreated SGD more expensively. So the first, and I think that just to repeat the comment for the purposes of recording, it's weird that you had to use all these tricks just to reproduce the performance of SGD much more expensively. So yes, it's much more expensive, but they don't say that this is what you should be doing. They're just asking the question in general, does deep learning only work because of the stochastic gradient descent? And the answer is kind of no, in their opinion, because look, you can make it work without the stochasticity and you can do full batch. It's impractical, you would never do that. But if you did that, you could still generalize well. So stochasticity is not necessary for generalization. That's the claim that they make. And then the second argument that they make is that this baseline SGD is actually an SGD that the community has worked on for several years. So a lot of the things are implicitly optimized for SGD to perform well. So the way we initialize has been optimized for SGD. And there's a lot of knowledge that went into designing various aspects of this SGD that you can think of as being equivalent to all of these different tricks that they had to use to make full batch gradient descent catch up with like, a decade of improvements. So whether you buy their argument or not is
I think it's particularly odd that they're introducing the variance of gradients, which is a product.
Yes, yeah. So I think this is why I don't like the title.
Yeah.
Because one of the other ways to read this result is saying, if you replace the stochasticity with this variance of gradient term, that gives you the same benefit as running the stochastic gradient descent. So maybe this model where the benefit of stochasticity is this variance of gradients term is actually a good model because we can get the same performance with the mathematical model as we could get with the stochasticity. So yes, you can, this is particularly interesting. And then you have to also, if between every subsequent gradient update, you also shuffle those mini batches. So when you calculate those gradient variances, you actually reassign data points to different mini batches. So again, you end up, this is now basically stochastic. You reintroduce some aspect of the stochasticity, you do even better. But that's, these experiments are super expensive and are not meant to be replacing SGD in any way. These are just illustrations of it being possible.
So another question. Did they try reordering the introduction of some of them who can't reorder? But I'm sort of curious. I'm almost like this is more like a decomposition of what the benefit effects are and what happens if you don't clip and regularize and do the
just regularize and not clip. And I don't think that they did. I think every single line in this table is probably costs a ton of time and a ton of money. So I don't think that they did all the different combinations of everything. They probably like introduced them one by one, and their goal was to get to the point where they can say, yes, it is it possible or not to match the performance of baseline SGD with full batch? And the answer is kind of yes, we managed to find one way that matches it. So to summarize today, gradient noise is a feature, not a bug, or at least that's how we think about it now. We used to think of it as something that's a necessary negative consequence of our hardware and other computational constraints, but it's actually something that turns out to be potentially beneficial for learning. SGD tends to avoid regions of high gradient noise. I think we have that intuition, and I don't think it's incorrect. And this may help with generalization. Another important thing to keep in mind is that there are a lot of different improved versions of SGD that you should use, things like Adam, but also be aware of the fact that they may not be the best for your problem, particularly from the perspective of generalization. And then also there are instances of optimization algorithms that people have developed and they turn out to be just too good, as in too good at optimizing, but at the cost of diminishing performance from a machine learning point of view. There is even a conference called I Can't Believe It's Not Better, where people kind of submit these methods that they derived and they came up with, which turned out not to work as well as they predicted. Some examples of this are improved optimization algorithms that actually don't work well in practice. Are there any questions? I will probably stop the recording.